Hello everyone, once again to this third lecture for EMC type wattmeters, where we're discussing about error in wattmeters. As we discussed in previous, that the one of the fundamental formula where we indicate that the theta, that is our deflection angle, is directly proportional. It is equal to it is equal to 1 upon k rp upon p dm by d theta. It will suggest that we will assume that this k 1 upon k rp and dm by d theta to be constant value. Okay, but now if we assume that it to be a constant, then deflection of a EMC type wattmeter having directly proportional to true power, and we indicate the true power in a real scenario. But practically this dm by theta is does not be constant at all with deflection, or the mutual inductance does not be constant throughout the all the deflection of the angle, and this rp angle, that is called overall resistance of an inductor, does not be wholly resistance. It should be some inductive part, or we can it affect the overall measure of the power. And so in this particular lecture we will measure different type of errors in electrodynamics. We will suggest the error due to the potential coil inductance, and we assume that it is only have a resistance nature of a nature only, but it have inductive effect only. How we compensate this pressure coil inductance? In third part we will indicate the its pressure coil not only have an inductance, is also having the capacity effects. What are the error due to the connection, or what we say when we connect the pressure coil in parallel to the load, or we connect it in parallel to the source. In third part we talking about the current errors, as we connected the AD current system, the how the AD current will causes the error in particular current coil. Effect of stray magnetic field, as we does not use the permanent magnet, we will use the electromagnet as if in a fixed coil. Error due to the vibration of moving system and temperature. These are the error we will discuss in today's lecture. Now start with one by one errors. First error is the error due to the pressure inductance. As we normally assume that uh, overall the pressure coil have resistance of rp, having the it is overall resistance with including of the external resistance. So we assume that ideally we assume that the voltage v that will be applied across the pressure coil, and the current through the basically pressure coil IP are in the same phase. If we assume it is a pure resistive system, but ideally in practical system, this particular connection, as we connected in the turn wise, this particular is act as a having some impedance. So it does not only have a resistive part, it also have some inductive part will act as a x of p. Okay, so voltage v is lead, or current ip lag the particularly voltage v by some angle theta. So this particular angle theta, or angle some inductive effect, how will affect the overall measurement, or we affect the error in the system, we will calculate in the system. Now as was suggested, ip is the current flowing through the pressure coil, and rp we assume is the only resistance of the pressure coil. Now we assume the second part, we will assume that there should be some additional system element, that is there should be inductance also in the pressure coil. Now in addition to this inductance, we have external resistance connected to pressure coil to increase the overall resistance system. Now the overall resistance rp, it should be combination of rp, small rp, inductance, and rb. All three element are being included to forming the total resistance rp. This rp is addition of small rv, rv and rp, and overall impedance is addition of this rp, resistance, and inductance L. Now there will be mutual inductance between current coil and pressure coil, and omega is the angular frequency. Now as I suggested, In previously, we will assume that voltage V and current IP are in same phase, but now we will assume that they have some angle phi lag between them. There should be phi lag between them, and normally V and I have lag of phi angle. We assume it's the loop should be inductive in nature. As we assume inductive nature, we have normally now this IP current and current flowing in current coil CC are have some angle between them, that is of phi dash angle lag between them. Now we have to see what will be effect of it. So inherently this effect of inductance of pressure coil is always be there in the pressure coil, and this alpha can be represented by tan inverse of imaginary value omega L and real value Rp, where Rp can be represented by capital small Rp plus Rb. It is a resistance of pressure coil and external resistance connected to it. Now uh, in previous in previous also, uh, if we relate Rp with equal to ZRP, okay, now this tan alpha is equal to omega L by Rp. Okay, now what will be causing the cos alpha? If we assume cos alpha, it acts as a power factor than Rp upon Z. So this then we suggested that Rp, the overall resistance of a pressure coil, can be indicated by Zb upon cos of alpha in the pressure coil. Uh, in from the previous in the previous formulas for a deflection coil, now we will replace all the similar thing. Now the overall formula should be VI RP cos alpha cos minus alpha upon dm by theta. Now this alpha value indicated the variation in overall angle deflection. Now without inductance, what should be our previous wattmeter formula? It is should be VI RP cos RPK cos phi upon dm by dt. It is a normal formula that will be our we are suggesting, but it is a modified indicating variation, indicating it is a formula for it. Now what should be the ratio? What is our previous formula and what is the error? What is a new deflection angle due to this angle alpha that we can calculate as true power indication upon the actual indication what we guesses. The true power what we wanted, it is VI RPK into cos phi upon dm theta. What we actually getting, that is VI RPK cos alpha upon cos phi upon phi dm by theta. Now that it is a friction formula that will suggested it causing the error. It is called also called, it is known as your correction factor. It is also called a correction factor. In figure 7 in the, it's also suggested that pressure coil during the leading load, the true power indicated actual wattmeter readings using a correction factor is equal to true power. When we wanted a true power, then correction factor can be multiplied with the actual voltmeter reading. So whenever we wanted some actual reading, that is called theta dash, we have to be multiply the correction factor, so we get theta value. Theta dash must be multiplied with the correction factor, it is cos phi upon cos alpha cos phi minus alpha. Okay, there is one of the thing what we getting, how we how we correct the particularly correction in error in potential coil. Now second thing, how we compensate this pressure coil inductance. One of the cases we have to be adding the correction factors. Now in this particular case, if there should be some inductance in the system, we have to provide some capacitance in series with your external load resistance system. Now we have a parallel capacitor arrangement in parallel with the external resistance RB. Okay, this overall small resistance R in parallel with C. Now, the overall system consisting as overall. Now, overall impedance of the system can be consist as RP, RV minus R, J omega L, R minus J omega C R square, 1 plus omega square C R square. Now, if we wanted only the real value term, when we assume that imaginary value, when we assume that the inductive part should not be there, so uh, we have to be zero the particularly your imaginary part. So in the particular case, omega c square r square in that particular case, it should be greater than 1. So total, we can write a total impedance formula should be overall impedance should be act like rp rv plus j omega l rc r square, whereby we providing the proper designing where L inductance L should be equal to CR square. So we will then we say that overall impedance only have a overall resistance of RP when L is equal to CR square. How we compensate the overall compensation of pressure coil inductance. Now, third thing, as we compensate the inductive effect in the your electromagnetic coil by using the one of the condition when inductance has to be equal to CR square. Now, one of the effects should be of pressure coil. When we suggested that how the capacitor should be working in any of the coils, having carrying some current, have some charges across it. This charges positive and negative current, having some air of as a medium. This act as a capacitor, having some EMF induced between them. This particular pressure coil also carrying some minor, having some small but carrying some of the capacitance value in it. This capacitance effect is mainly due to the, as I said, internal capacitance of winding and external resistance. It is very small. It is very small, but it will cause a small error in the system that can be caused when we read the small power. It can causes the vary the true value very much. So that this effect of stray capacitance of pressure coil is opposite that of inductance. In case of your in case of when we have a inductive effect, it will lower down the power, where in case of C it will increase the overall power. Okay, now in case of leading and lagging, both act as a different. So therefore, when we wattmeter low on lagging power factor and high on leading low power factor of the load. Okay, actually the reading of wattmeter does once again need to be corrected by corresponding correction factor to obtain the true value, the effect of worry. So in case of lagging load, wattmeter lead low. In case of lagging load, lagging power factor. In case of leading power factor, it acts as a high. Okay, so it has a inverse effect. As we see in the inductive effect, it has an inverse effect. If the pressure co-inductance during the leading load have to be corrected. Now, fourth point, it is error due to connection. As I suggested previously also, the connection when the pressure coil is connected across the source and pressure coil when is connected across the load having a different effect. If the pressure coil is connected across the your source, then this current coil having some any small resistance causes some voltage error, VCC voltage drop, causing the overall voltage whatever the pressure coil is measuring should be getting error. When we connected the pressure coil connected across the load, then there is some small current should be consumed by this pressure coil, and the overall current measured by this current coil should be getting some error. So this whole both connection can be carried out the getting error. Okay, so as I say, in case of when we connected it power loss in CC coil, when we connect the particularly your pressure coil across the source, when we connected your pressure coil across the load, then power loss in system. So how it can be occurred. We will suggested that pressure coil when connected to supply, there is a carried some load and plus current coil system. Okay. uh, so how should we reduce this particular losses? We will reduce this particular losses, as I say in previous case also. We have to be always be suggested that when we connected the pressure coil against the source, this RCC, there is small resistance RCC, should always be very smaller than load resistance RL. We have to be suggested that when the pressure coil is connected across the load, then pressure coil should be very high than load. In that particular case, we suggested errors due to the connection can be reduced only. Now, effect due to the AD current errors, as is suggested that both fixed coil or a moving coil system are being binding on some core. This core, when we assumed to be some thick metallic part, this if magnetic field will be made due to the current AC current, the magnetic field be alternating system. So this alternating magnetic field causes some AD current in this particular course, and this AD current causes the power losses, overall power losses, as we assume this power losses carry the eddy current losses in the system. So this eddy current produces a spurious magnetic field of their own and distort the magnitude and the phase of the both current coil and as well as the your pressure coil of the system. So error caused by eddy current is not easy to estimate, as we does not know how much current to be they made. So if metal part are not carefully avoided from the near of the current coil, so in fact this solid metal part in case of coil support or weakens as case of a core should be minimum as possible, and in case of core we have to be staggered them in for a low less. So the high resistive, any metal that is kept away and selected to have high resistivity to reduce the eddy current in the system. Now, against sixth part is stray magnetic field. As we say, the electromagnetic EMC instrument use the not the fixed magnetic field. So some external magnetic field can causes the error. So shielding against the stray magnetic field can be very important. So laminated iron shield are made in portable laboratory instrument. Steel casing are provided as a shield in switchboard mounted measurement devices to reduce this type of error. But most importantly, introduce the error, but in this particular cases also introduce some type of eddy current errors. So we have to be choose whatever be important, stray magnetic field losses are greater or eddy current losses are greater. So also some DC error due to the permanent magnetism of magnetic shield influence the external magnetic field. So one of the suggested diagrams are should be there, where we provided some external shielding toward them. Okay, the overall aesthetic of this EMC instrument are constructed with two similar sets. As we see in diagram, the pairs of these are connected to produce a magnetic field to oppose the system. So net magnetic field is to be 0. The last part would be vibration of system. As we know, the instantaneous torque of a moving system is very cylindrical as a torus of frequency, as you see 2 omega t part. If any part of the moving system is like a spring pointer has a natural frequency close to the torque pulsation, then they will vibrate and on a resonance frequency. This vibration causes an error or nothing pointer position should be worried. This error to the vibration may be avoided by designing the element having not natural frequency further away to the choice of supply frequency. Okay, and last, that is a temperature error, as the spring or a other equipment having some resistance can affect its value. Like spring can be stiff, or the resistance of a values of a pressure coil and current coil can be varied due to resistance. So high precision instrument are being used. Thank you so much for this particular part where we study different type of error in EMC type instrument. In next part we will discuss about the application of this EMC type instrument. Thank you so much.